you remember doing the orbital diagram, this is what carbon looks like as an atom. But now when it's in a molecule and it has other attached atoms, it hybridizes or mixes together these atomic orbitals to make these new hybridized orbitals. And that's what's actually showing up in the structure you draw from the dot structure. Hybridization just means this. Okay? Do you remember how many orbitals are in the sublevels? Like the S sublevel has one orbital, the P sublevel, 3, the D sublevel, 5. Okay, great. So I also say, it takes as many atomic orbitals as hybridized orbitals you need to make. So if you draw your structure, you say, oh look, the coordination number's 2. That means the hybridization has to add up to 2. In other words, I need 2 atomic orbitals to make 2 hybridized orbitals. Well, I'm always going to take one orbital from the S. The P sublevel has 3 orbitals, but I only have to use one of those. If I mix one S and one P orbital, I can hybridize them and call it SP hybridization. One S, one P orbital. And then that's when Vesper theory kicks in. How do you separate 2 hybridized orbitals as far apart as you possibly can? You go to 180 degrees, right, and you get a linear shape. Okay, once you see the pattern that's at work here, hopefully it'll make good sense. So you do the dot structure. You look and you say, oh, the coordination number is 3. That means the hybridization has to add up to 3. So I need one S and 2 P orbitals. So they call it sp2 hybridization. I'm going to mix one S orbital with 2 of the P orbitals to make 3 hybridized orbitals. And then Vesper theory kicks in. How do you separate 3 hybridized orbitals as far apart as possible? 120 degrees, and you get that trigonal plane shape. When I was talking Vesper theory yesterday, I just didn't use the word hybridized. You're really separating hybridized orbitals. Can you guess where we're going next? Right, what if you do the dot structure and you say, oh, the coordination number is 4? Then the hybridization has to add up to 4. 1 S, 3 Ps. I'm going to hybridize, mix 1 S and 3 P orbitals together. I get these 4 hybridized orbitals. And how do you separate them as far as possible? At the equal, 109.5 degrees. And you need a hybridized orbital if you're attaching to an atom or if you have a lone pair. Attached atoms and lone pairs have to be in a hybridized orbital. Didn't we start to look at standard octet yesterday? Did we do like PBR5 or something? Yeah. Okay, so it is possible your center atom could have more than 8 valence electrons. And that's when you have to start bringing in the D sublevel. So remember, if you get to the 3rd row or lower, that's when the D sublevel starts to exist. Like if you say n equals 2, there's no such thing as a D sublevel. There's no 2D sublevel. So elements up in the 2nd row, like nitrogen and oxygen, they don't have D orbitals to use. But if you get down to the 3rd row, phosphorus, sulfur, chlorine, anything below that, there's D sublevel orbitals that are available. So if you guess the coordination number is 5, now you need 5 hybridized orbitals, 1 S, all 3 Ps, and a D. What did you say? She is not here. Okay, what was this? Oh, I was going to say this. So if the coordination number is 5, you need 1 S, states and one D now, we call it sp3d hybridization. Or as you can guess, the coordination number could be 6. Now you need 1s, 3 p's, and 2 d sublevels, 2 d sublevel orbitals, so it's sp3 d2. How am I doing on this one? So again, that's one reason why I like coordination. Helps pin down with the hybridization. That's the attitude. And this isn't Schoology, obviously. You can look back at it if you want. I don't know what you said.
So the coordination number is 5 and 2 has
Because you need 5 hybridized orbitals. 1s, 3 p's, and 1 d.
and hybridizes those orbitals together.
Right, it's the atomic orbitals we're mixing together to make the molecule, essentially.
When they're asking for the bond angle, like for sp3d, I should just try to get 90 right?
Right, but we gotta talk about that. And you gotta add on to where we quit yesterday. Essentially, yes.
So hybridization is the mixing of orbitals with
True. Right, it's hybridization is all about the center atom trying to make the molecule, right? It has to attach to some number of atoms, it might have one pairs there. The hybridized orbitals are weird. The attached atoms don't have to hybridize, they don't have to. Okay, so okay? Then, the other thing I was gonna throw in before we started to finish the shape stuff. Yesterday, we talked about resonance, you may recall, and we were talking about sigma and pi bonds. And I didn't try to explain really the difference between them, but I do like to show you what's going on there. So hang on a second. I've got a picture for that. Remember your orbital count? Like it was yesterday. Ethane, remember A-N-E-N-E, that single bond between carbon atoms? Okay. So an ethene molecule, these 2 carbon atoms hooked together with a single bond. If you look at a given carbon atom, it has 4 attached atoms, which means the coordination number is 4, which means the hybridization is sp3. And you get that nice tetrahedral shape. Okay. Now, I'm imagining the carbon atoms trying to share electrons with each other. So these are the hybridized orbitals, right? They're in that tetrahedral shape. The carbon atoms can align themselves so that these hybridized orbitals overlap end to end. And what's significant is the electrons are being shared directly between the carbon atoms. That's what makes a signal. Okay? Think about the bonds between carbon and hydrogen. Look where the shared electrons are directly between the carbon and the hydrogen atom. A sigma bond is a stronger bond because you might say those electrons are protected. They're buried down in, they're right along the axis between the 2 atoms. Sigma bonds are always strong. Good so far? All right. Then think about ethene. Remember the E and the N, you meant there was a double one. So now you draw it like that. So when you look at a carbon atom, it has 3 attached atoms. That means it's sp2 hybridized because the coordination number is 3. That gives you that nice trigonal planar shape, right? So, here are the hybridized orbitals for the carbon atom. Right, trigonal planar shape. Again, I can imagine the carbon atoms aligning themselves so the hybridized orbitals overlap end to end. That's what makes them similar. Okay? The hydrogen atoms, the shared electrons are right between the carbon and the hydrogen atom. Similar. But there's one p orbital that's not hybridized. Because there's 3 orbitals and we only use 2 of them. Here are the unhybridized p orbitals. You notice how they're parallel to each other. And so what they imagine is those p orbitals can overlap side to side. And that's where the sharing is occurring to make the pi bond. Let me show you a little different picture. There's a little bit different representation of it. The purple is the hybridized orbitals. Right? Here's the green hydrogen atoms, a sigma bond, sigma bond. Here's the unhybridized p orbitals. Again, they're parallel to each other, but they imagine that they overlap side to side. And so the significance is the electrons are being shared in a region of space that's not directly between the 2 atoms. Pi bonds are not as strong. You might say the electrons are hanging out in space, so to speak. They're not nestled down in here between the 2 atoms. Right? There's a difference between sigma and pi bonds, how the electrons are being shared. Are you going to ask about this on the EP test? I have no idea. Fortunately, you don't have to know this. If you're looking at this and you can say, oh yeah, this double bond has 1 sigma and 1 pi bond. And you don't really have to not necessarily understand that. Let me get a landing means on it. Okay, say again if you get a question. Ian, what were you going to say?
So the who of those orbitals is a single atom?
Yes. Now this is what's weird about quantum mechanics. There's 2 electrons being shared somewhere in these blue regions. I don't know where they're at. And in theory, they can't be in between somewhere. So if they're here and then they show up here, how do they get there? I don't know. That's the mystery of quantum mechanics. Are you looking, what color? Are you looking at blue? Yeah. Yeah, this is your p orbital side-to-side overlap. This is your pi bond. But you're overlapping in 2 places, but it's just 1 pi bond. Let me show you one more picture. This is nitrogen. Okay. Nitrogen atoms form a double or a triple bond. Okay. Now, because they're going to attach to another atom, they have to hybridize. And so they sp hybridize. You can imagine them overlapping end-to-end sigma bond. But now there's 2 p orbitals that have not been hybridized. Right, so there's a pair that are like this, maybe, and then you have to imagine a pair that are going in and out of the stream. Right, so these guys that are in this direction are overlapping like this, right, above and below the axis of the nitrogen atom. One second there, and then there's another pi bond. There's a shared region in front and behind the stream. That's the second pi bond.
Do we have to like draw these?
Good as no.
Okay.
No, don't have to draw. Thankfully, that's why I'm showing you pictures, because I'm not going to draw. Have I said enough to sort of have an idea of the difference between sigma and pi bonds? That's my goal.
feel like I could visualize it with like your words, even if I didn't see the picture.
Yeah, that's possible. You know, some people are like visual learners, some people are, say, auditory learners, and there's different learning styles. All right. Yeah, okay, then on with the shape show. I think in sixth hour, didn't we get all the way through trigonal bitrigonal? Did we do like
Yeah.
PBR 5 or something?
Yeah, we did trigonal bipolar.
And we got all the way through everyone?
Yeah, we did the trigonal bipolar.
That's very good. Okay, now the coordination number 5 family is the biggest. There's actually 4 members to the family. Okay, so we gotta keep going. Right. Let's think about POF3 minus 2. And I'd like to run through the dot structure on this one, just so I can show you one thing. Do you want my phone? You
Yeah,
wanna plug
sure.
it in?
Yeah, get me on there.
One second.
I am grading the Fund 1 test notes. See if anybody has.
But like, if you, I think if you study for the Chrome 1, it's easily passable. Yeah.
No, I don't think I would.
I was down.
But I was
Oh, what?
Yes.
Solid to gas.
That's
Big,
easy.
flop the straight.
So, ice, if something goes ice, that's
Exactly, yeah.
You're not that.
Oh, it's not.
You're not passing.
Solid to gas.
Girls not
And that's all, it's not gonna be hydrogen.
Why are you still recording? This is going either or zero not passing. If he is going in not passing.
Arthur, you're definitely not passing.
I'll get my brother to help me. I'll get my brother. He'll be next.
Did you even get a 4? I'm scared for you.
I'm scared for you.
Well, my brother's gonna beat him.
Okay. One thing on the
I know, I saw this picture, but I was like, yeah.
it's okay.
I was like, it was like,
What? I got an 84. But he beat Street Big.
You have 84 It's not
Oh.
Okay, so
Oh wait, I'm talking about this big one? Oh.
here's what I wanted to show you with this. Well, first off, you guys feel good about doing dot structures?
Yeah.
Okay, so that's great, but let me kind of run through this one just so I can show you one thing. Okay, so there happens to be, let's see, 3 times 7 is 21, another 5, 26, another 6, 32, and then it's minus 2, 34 electrons. Who do you want to put in the middle, phosphorus or oxygen?
No.
Oh, phosphorus, oxygen?
Phosphorus.
Okay, if you're uncertain, go with the lowest electronegativity element.
Yeah, phosphorus.
Phosphorus is lower electronegativity than oxygen. Okay, so you probably would do this then. Okay, we just used up 8 electrons. So now we're down to 26 left. The attached atoms all need 6 more electrons. Okay, so I could do that. Now that used up another 24 electrons. And now I have 2 left. And this is really the point I wanted to make to you. You get to the end, I satisfy the octet rule. Everybody has 8. But I still have electrons left. There's only two possibilities. I either miscounted electrons in the beginning, and somehow I ended up with 2 extra, or it's an expanded octet structure, and those last 2 electrons must go on the center atom. Okay? come up with extra electrons at the end, and you satisfy the octet rule, those extra electrons are gonna be on the center atom. Sometimes I have people mistakenly say, oh, does that mean there's a double bond? Well, a double bond is working against you because it's creating more sharing. It actually means you need less electrons. If you get to the end, you use all your electrons and the center atom is short on electrons, then you gotta think double or maybe even a triple bond.
So basically, if someone get an upgrade, I can put electrons on it.
That could be one way to say it. Now, of course, this is a general formula of 8x4 1. That's why the coordination number is still 5. Okay, the hybridization, S, P, 3,
D.
D, right? Is that would add up to 5?
Yeah.
Now we gotta come up with a name for this thing. So then you need to know this. The coordination number 5 family has the most little quirkiness about it. So when you look at this molecule endwise, there's 3 going around. They call those equatorial atoms. And then there's these that are top and bottom, they call those axial atoms. And the coordination number 5 family, if you have to take off an atom, always take off an equatorial atom. Take off the ones going around like this. That's what I'm going to do. Pop one of those off. Okay, now we're looking for a name for this thing. And if you set it on its side, it tips back and forth, like the old playground favorite, the seesaw. And that is indeed the name for this seesaw. And can you imagine this lone pair, space hog, pushing these atoms backwards a little bit? So now the angle's probably a little less than 90, it's a little less than 120.
So if you have something and you have extra electrons, but the center atom doesn't have like the oxide and stuff like that, so there's more bonds, but then if the center
Well,
atom.
but did you say at first extra electrons?
Wait,
If you get to the end, right, if you've done your structure, if you've used up all your valence electrons are gone, and the center atom still needs more electrons, think double or maybe even a triple bond.
but then if you have extra and the center atom already has all its oxide and its oxide,
Then you add in that extra pair to the center atom. Does that help you?
Wait, is it just called seesaw?
It is. Seesaw, very technical name. Seesaw. And the angle is a little less than 90, and it's a little less than 120. What do you think? Seem okay?
Yeah.
Yeah.
Yeah, it seems okay.
Okay, so if you start with trigonal bipyramidal, okay? You know, these 3 going around are called equatorial. Are you okay with that? And these are axes. So in trigonal bipyramidal, you always take off one of the equatorial atoms. Don't take off an axis.
Hey, you better not take all that.
Well, because when I look at my structure, I've got 4 attached atoms going on there. All right, what do you think about seesaw, Elena?
I love that.
So you always take off the equatorial.
Always take off an equatorial.
I think like, I took off an axe line.
Yeah.
Hey.
Okay, you ready for the next one?
It's jumping like a price because I'm going to go
Okay, let's see.
So.
Okay, here's the next one. CLF3. CLF3. Now again, resist the temptation to shortcut the process, right? Because I know I've had people do this, they look and go, oh, it's a center atom with 3 attaches trigonal plane.
That's probably wrong.
Probably wrong because you don't know if there's lone pairs. It's the lone pairs that'll get you if you try to shortcut the process. And so indeed, when you draw this thing out, and if you want to go through it in detail, you can. You'll have the 3 fluorines attached, but you'll find you also have 2 lone pairs. And so now the general formula is AX3E2, which is why the coordination number is still 5. Which is why the hybridization has not changed. What do you need a different name? So again, start mind's eye, trigonal bipyramidal, take off 2 equatorial atoms. You get this, and then you're struggling for a name, so turn it on its side.
That's not
Turn it on its side and think letters of the alphabet, and you get
W.
T-shape. Oh yeah, W. Yeah, that's what I think. Yeah, you're gonna get T-shape.
So is our shape literally T?
Yeah, it's called T-shape.
That's it?
That's it. Now, what do you think about the bond angle? It's a nice perfect 90 degrees.
I would agree with that.
Yeah.
I don't know. I'm imagining these lone pairs maybe could
They're pushing it
do
back.
a little
I forgot
pushing.
lone pairs.
Yeah, yeah.
Okay, so we should say less than
It's
that.
probably a little less than 90. Who cares what the exact number is?
I don't like that.
Oh, I didn't write shape. That's T-shape. Oh, thanks. Okay. All right, coordination number 5 family is the biggest. We still have one more number one family.
Yeah, I said that. I would feel bad. Like, genuinely, Ali was like, I was like, if all my answers are that's not, I'm over your track.
All right. I3 minus 1. I3 minus 1.
So that's
When you do the
24.
dot structure, you will get this. Okay, you get to this point, and then you'll end up with 3 lone pairs on that middle item.
Wait, is that 22? That's what
It is 22. Yes, sir. So the coordination number is still 5 because the general formula is AX2E3. Of course, the hybridization hasn't changed, but the shape has changed. So now, we're going to take off all 3 of the equatorial atoms. Like this. It's not a snowman. Somebody earlier today said snowman. Mutant snowman with okay, it looks like a, not bouncing. It's linear. It's a nice straight line, it's linear.
Well, what about the lone pair with that?
Now, in this case, what do you guys think? Are we gonna keep a nice 180? I've got 3 lone pairs, they're all going around like this.
Oh, they're pushing all against each other.
I
So
think
it
they end up
stays at-
fighting each other.
Yeah, so it stays at 180.
Yeah, I think it's a nice 180. Yeah, so linear, nice 180.
How do you pass the job?
Now again, you guys, the first 6 shapes we talked about are the most common, right? Because the center atom has 8 valence electrons. These can happen, but they're not very common.
So why is it?
Because it looks like a straight line. Say that. But the electrons, lone pairs of electrons, I refer to them as the invisible force. They're there, They take up space, but they're invisible when you name it. It's all about where the atoms are. Does that help correct it?
There's always like electrons on this upper one, when you push it away from the electron.
Well, I just remember that lone pairs of electrons are spacewalks. They take up a little bit of extra room. So, given a chance, they can push attached atoms a little bit out of position. But sometimes they end up fighting each other. Just how things are working. Are you ready to meet the final thing?
Yes.
Final thing. Okay, let me put just triangle lights here a little. Okay. Here we go. SF6 could be an importance. As you can imagine, you end up with a sulfur atom with a 6 fluorine atom surrounding it. And of course, I am not attempting to draw this in any kind of manner that shows what it might look like. I'm just throwing it out. And by the way, I may have said this yesterday, but the book does have some pretty good pictures, pages 394 and 395. If you are a visual learner sort of person and you like pictures to look at, the book has pretty decent pictures.
I like pictures.
Yeah, I can't attempt to draw, so I'm about it. So, here we go. Again, Vesper theory, right? I've got general formula of AX6, coordination number 6, hybridization should be S, P, 3D2, right? Have to add up to 6. And this is how you spread them out as far as possible. Look how symmetrical it is. Pretty much looks the same any way you twist it. Because the bond angle is always 90 degrees. And same bond angle, so it's very small.
That's the
But we need
shape.
an 8.
That's the shape.
Yes, sir. No, good try. Although it is sort of two pyramids sitting base to base. Right? But here's the strategy behind the name. You know tetrahedral, right? 4 tetrahedral. That's a 4-sided shape. 4 sides, tetrahedral. How many sides does this have?
6.
More than that.
7.
Somebody said it. It has 8. There's 4 sides up top.
Oh.
There's 4 sides on the bottom. You can imagine 2 4-sided pyramids sitting base to base. So if there's 8 sides, octahedral. Octahedral. It seems like a weird name because there's 6 attached atoms. You might think there'd be hex something or other. That shows up in the name for the molecule like sulfur hexafluoride. But if you're going to name the shape, it's octahedral because they are saying there's 8 sides to this thing. There we go, octahedral. See that? All right, are you hanging in there? We got 2 more shapes to go now. 2 more shapes to go. Here you go. CLF5. CLF5. Oh, I bet it's trigonal bipyramidal. Center atom with 5 attached. Well, sort of. Alright, you will get to this point, you'll have your 5 fluorines attached, but you're going to find out you have 2 extra electrons. It's because the chlorine has a lone pair.
So you have to add
So it is X5E1. Remember what you said?
No, I would say you have to add the E1.
Yeah. So it's still going to be coordination number 6. It's still going to have a hybridization of sp3d2. What do you rename? Now we could take off any atom we want to start with because it's so symmetrical, right? So I'm just going to pop off one atom. I'm going to orient it like this. I see 4 going around. That makes me think of a shape. No, it tries. Starts with an S, ends with a U, there's a Q on it. Square. And if I was in Egypt, I might see this. So the name for this is square pyramid. Square pyramid.
That's pretty simple.
And what do you think about the bond angle? It was a perfect 90, but this one pairs down.
That's
So as you can imagine, right, it's going to shove these atoms up just a little bit. So the angle is probably less than 90. And what's wrong with this? Oh, I switched it before. Bond angle is less than 90, and this is called square pyramid. Man, what do you think? Killed Sakina a while ago. Elizabeth is almost out of it. She's close. I wanted to maintain, I need to wire the chairs and give it a shot. Oh yeah, C3. Oh,
You do that when there's a question.
there you go, you got it. It's a corporal punishment method. My wife went to a Catholic school, so she always likes to talk about one of the math things she had. Sister Claudette. And they had a quiz every single day. And so they called her Sister Claw, or just the Claw. You can just imagine this woman like, that's a wrong answer, Jake. Crack you over the head with 2 by 4s. Okay. You don't see noble gases in very many compounds, but xenon tetrafluoride does exist. You have to heat the gases to some absurdly high temperature. I mean, it's not easy. And again, my last shot at this, resist the temptation to go, oh, it's probably just a tetrahedral, center atom with 4 action. Because guess what you'd be missing? Lone pairs. Okay, so you may start this way and have this drawn, but then you find out, oh, I got 4 extra electrons left over. And that's because the xenon atom has 2 lone pairs in it. Which means it is A plus 4 E2. Coordination number still 6. Hybridization still sp3d2. A new name. Okay, so now it does matter which atom you take off, because you want to give the lone pairs as much room as possible. So pop off the top one.
I was just top off. I
So
can
square?
bounce out.
And everybody is flat. It is called square plane.
Oh, I got it.
Square plane. Oh, I should have said bond angle. Are you imagining a bond angle of 90 degrees? Because the lone pairs are just fighting each other. They're directly opposite each other. So we're back to 90 degrees. Square plane. And you are done with the shape shot. Yes.
Square,
They got us all this other stuff. Lone pairs are the curse of resistance. All right, so if you think about what we've accomplished here in a short amount of time, chapter 8 is all bonding stuff, as well as chapter 9. I think in chapter 9 you see things like hybridization. It's all bonding, chapters 8 and 9. Chapter 10 is about intermolecular attractions, like dispersion forces and dipole-dipole attraction. The good news is you guys have already have some experience with that. But we're going to have to run through it. They love to ask questions about intermolecular attractions.
I got a bunch of like ion and dipole attractions.
Yeah. On one of the practice things?
Yeah.
Yeah, they love those questions. So it definitely is a good thing to know how to do. So Monday, of course, we got the review quiz. Tuesday, we'll have to wrap up with intermolecular attractions. Next week's crazy, right? We got 3 assessments. You know, if you keep your sanity through next week, you're doing a great job. There's still going to be some things. We have our bonding test on Friday the 25th, next Friday. There's still going to be a few loose ends to tie up. We should talk about photoelectron spectroscopy. I couldn't fit that in chapter 7. They like to ask about chromatography. Yep. And so I should at least do a demo for you so you know what that means. They like to ask lab questions. So it actually is worth it to think about the labs we do.
Did we already go over lattice energy as well?
We have not done lattice energy, thank you for reminding me. We should stick that in as well on Tuesday.
Wait, look at this. He's so much.
So my very last thing to say to you guys today, for the review quiz Monday, right, it's 2 topics, right, gas laws and electrochemistry. Hopefully the electrochem stuff is sort of fresh in your head. It's been a while since we done gas laws. That was chapter 5, very end of the first quarter. But I wanted to point out to you that they love also to ask gas law questions. Those are favorites. So it's worth, you know, going through the gas law stuff and having a handle on it. That will definitely give you a great review. I'll give you pumped up for Monday's review.
Give me a little tax return on me.
There you go. A little love from the IRS. So, good luck. Elena, were you going to say something else?